China is no longer showing the world another flying car concept. A factory in Guangzhou has already begun trial production of one. The first aircraft has rolled off the assembly line. The manufacturer says thousands have been ordered, and the factory is designed to produce one flying module every 30 minutes when operating at full capacity. The machine is called the Land Aircraft Carrier, and it may be the closest anyone has come to turning the flying car from a technology show fantasy into a real consumer product. It does not grow wings while moving through traffic. It does not launch from the middle of a crowded highway. The system is much more practical than that. A six-wheeled electric vehicle carries a compact aircraft inside its rear compartment. Drive to an open launch site, press a button, and the aircraft separates from the vehicle before taking off vertically. The company behind it plans mass production and deliveries beginning in 2026. If that happens, China will not simply have built another experimental aircraft. It will have created the first modern production system designed to manufacture personal flying vehicles at something approaching automotive scale. And that is why this story matters. Flying cars have appeared at technology exhibitions for more than 50 years. Companies have built prototypes, released beautiful computer animations, collected deposits, and promised that traffic congestion was about to become a thing of the past. Then almost all of them disappeared. Some vehicles were too heavy to fly efficiently. Others were too fragile to drive safely on normal roads. Many could not satisfy aviation regulations, and almost none could be manufactured at a price normal customers would accept. China's approach is different because it does not force one machine to perform two completely different jobs. The Land Aircraft Carrier is actually two vehicles working together. The first is a large 6x6 ground vehicle the company calls a mothership. The second is a compact electric vertical takeoff and landing aircraft stored inside it. One vehicle handles highways, charging, luggage, bad weather, and long distances. The other does only one thing: fly. Separating the two machines may sound less futuristic than a car transforming into an airplane, but it solves one of the biggest problems that has kept flying cars trapped in science fiction. This video is going to explain exactly how the system works, why China is moving so aggressively into low-altitude aviation, and what still has to happen before ordinary people can actually use one. No pretending that cities will be filled with flying cars next year. No treating a company's production target as proof that every vehicle will be delivered. And no ignoring the safety, battery, airspace, noise, and certification problems that could still delay the entire project. The real story is more interesting than the marketing. China has built an industrial strategy around the idea that the space above cities could become a new transportation layer. Just as highways, high-speed rail, and electric vehicles created new transportation systems on the ground. XPENG's flying car company, now known as Airage, is building the consumer vehicle. EHang has already achieved important certification milestones for a pilotless passenger aircraft. Local governments are constructing operation sites and creating low-altitude development plans. The machines are different, but together they show something important. China is no longer asking whether electric urban flight is technically possible. It is trying to determine whether it can be manufactured, regulated, and operated as an industry. To understand why the modular design is so important, imagine trying to build a vehicle that is both a safe family SUV and an efficient aircraft. A road vehicle needs heavy crash structures, large batteries, comfortable seats, suspension, tires, doors, lights, and enough strength to survive years of potholes and collisions. An aircraft needs almost the opposite. Every kilogram matters. The body must be extremely light, the shape must move through air efficiently, and every component that does not help the vehicle fly becomes a penalty. Adding stronger doors might make the road vehicle safer, but shorten the aircraft's range. Adding large wings might improve flight efficiency, but make the vehicle impossible to park. Folding systems add mechanical complexity, weight, and new failure points. Engineers have spent decades discovering that a good airplane usually makes a terrible car, and a good car usually makes a terrible airplane. The land aircraft carrier avoids that contradiction. The ground module never flies, and the aircraft never drives through traffic. Each can be optimized for its own environment, while the customer still transports both vehicles as one system. It is less like a car that becomes an airplane and more like a mobile private airport, carrying its aircraft wherever the owner wants to go. The ground vehicle is almost as important as the aircraft. AirEdge describes it as a six-wheel, all-wheel drive carrier with rear-wheel steering, designed to fit into standard parking spaces and access underground garages despite its unusual size. It uses an 800-volt silicon carbide range-extended power system, and the company claims a combined driving range of more than 1,000 kilometers under China's CLTC testing method. The carrier also functions as a mobile charging station. AirEdge says it can recharge the aircraft while parked or driving, and can provide enough energy for as many as 6 flights after the system has been fully charged. This solves a problem most flying car presentations barely mention. An electric aircraft landing in the countryside is not useful if it needs a specialized high-power charger before it can fly again. By carrying fuel, batteries, power electronics, and charging hardware in the road vehicle, the system takes part of the aviation infrastructure with it. The owner does not need a complete vertiport at every destination. The mothership becomes transportation, storage, shelter, and energy supply for the aircraft at the same time. When the owner reaches a suitable location, the rear of the carrier opens and the aircraft automatically separates. Official XPENG material says the air and ground modules can disconnect or reconnect in less than 5 minutes using a one-button mechanism. The aircraft then unfolds its arms and propellers and prepares for vertical takeoff. AirEdge describes the flying module as using 6 rotors with a dual-duct configuration and foldable blades and arms. Unlike an airplane, it does not need a runway. The rotors push air downward, lifting the machine vertically in the same basic way as a helicopter or large drone. This makes it suitable for open fields, designated launch areas, tourism sites, and specialized low-altitude camps. The company is also developing manual and automatic flight modes with simplified controls intended to reduce the amount of aviation knowledge required from the user. That sounds revolutionary, but the word simplified should not be confused with risk-free. Flying remains completely different from driving. Wind changes in 3 dimensions. Landing areas can become obstructed. Battery reserves must account for emergencies. A person who makes a bad decision in a car can stop beside the road. A person who makes a bad decision in the air still has to land. That is why the real breakthrough is not the shape of the aircraft. It is the attempt to make aviation behave more like a consumer technology product. Traditional private flying requires an airport, a licensed pilot, aircraft maintenance, fuel management, weather planning, and continuous training. Those barriers explain why personal aircraft never became as common as cars, even in wealthy countries. AirEdge is trying to hide much of that complexity behind software. Instead of controlling every aircraft surface directly, the user gives the machine a simpler movement command, and the flight control computers translate it into adjustments across the rotors. Automatic modes could handle takeoff, landing, route following, and stability. Sensors monitor the aircraft, while software corrects small disturbances faster than a human pilot could react. This is similar to what happened with modern drones. Flying a traditional radio-controlled helicopter required enormous skill. A consumer drone uses computers to remain level, hold position, return home, and avoid some obstacles. The user feels as though the machine is easy to fly because the software is performing thousands of difficult corrections invisibly. China's flying car companies are betting that the same transition can happen with passenger aircraft. But carrying a camera is completely different from carrying a human being. A consumer drone can crash without turning into a national aviation disaster. A passenger aircraft cannot. Airage says the land aircraft carrier uses redundancy across propulsion, energy, high and low voltage power, navigation, communications, and flight control systems. XPENG has stated that the 6-propeller arrangement is designed so the aircraft can continue flying and land safely after failures involving 2 diagonally positioned rotors. These are company claims that must be verified through the formal airworthiness process. Redundancy sounds simple, but it creates difficult engineering questions. If one motor fails, does the remaining system have enough power during hot weather and maximum weight? If a battery module develops a fault, can it be isolated before damaging the rest of the pack? If satellite positioning is interrupted, can the aircraft navigate safely? If a communication link disappears, does it return, hover, or land? Every backup system adds weight, and every kilogram added for safety reduces payload or flight time. Aircraft engineers constantly balance these competing requirements. A successful flying car cannot merely survive normal operation. It must remain controllable when something abnormal happens. This is where China has already achieved something the rest of the world cannot dismiss. Another Chinese company, EHang, developed the E216S, a pilotless electric vertical takeoff and landing aircraft designed to carry passengers on preset routes. In October 2023, it received a type certificate from the Civil Aviation Administration of China. It later received a production certificate and standard airworthiness certificate. In March 2025, 2 operators received the first Chinese air operator certificates for commercial passenger-carrying pilotless aircraft services. EHang said these approvals allowed customers to purchase tickets for low-altitude sightseeing and tourism flights at approved operating locations in Guangzhou and Hefei, with other uses potentially expanding according to operating conditions and regulatory approval. This does not mean autonomous air taxis are flying freely between every Chinese office tower. The early services are tightly controlled, route-based, and limited to specific sites. But certification matters because it separates aviation from almost every other technology industry. A prototype demonstrates that something can fly. Certification demonstrates that a regulator has accepted a defined design and operation under specific conditions. The EH216S went through more than 1,000 days of certification work. EHang reports that the process involved more than 500 assessment subjects, over 40,000 flights used for testing and adjustment, 65 major certification categories, and more than 450 formal conformity verification subjects. Tests covered structural strength, materials, fire resistance, crashworthiness, software, data links, flight performance, electromagnetic compatibility, navigation, ground control systems, and environmental conditions. The aircraft itself is designed for preset pilotless routes, has a published range of 30 kilometers and a maximum design speed of 130 kilometers per hour, and uses centralized ground systems to monitor and manage operations. These numbers reveal why flying cars cannot follow the normal consumer electronics development cycle. A smartphone company can release a new device every year. An aircraft manufacturer may spend years proving that one configuration remains safe across thousands of scenarios. Changing a motor, battery, propeller, or software system after certification may require additional evidence. The product cannot simply be updated whenever the marketing department wants a new feature. Aviation moves slowly because every major change can create a new failure mode. The land aircraft carrier and the EH216S represent two different paths into the same future. EHang is building something closer to an autonomous air taxi. The passenger does not own the aircraft or control the route. A commercial operator manages the machine from approved locations, much like an airline or sightseeing service. AirAge is aiming at a more personal experience. The owner drives the carrier to a suitable location, deploys the aircraft, and uses it for short recreational or local flights. The first model is unlikely to replace the daily commute through central Beijing or Shanghai. It makes more sense around scenic areas, private properties, remote regions, tourism routes, flying camps, and places where open landing areas can be controlled. This is a smarter starting point than immediately filling crowded cities with aircraft. Rural and tourism environments have fewer buildings, less complicated traffic, more emergency landing options, and lower population density beneath the flight path. AirAge has announced plans to work with the Dunhuang government on a low-altitude tourism route, showing that the first business model may look more like adventure travel than urban transportation. That may disappoint anyone imagining a flying car parked outside every apartment, but almost every major transportation technology begins in a limited environment. Early automobiles were expensive toys used by wealthy buyers on roads built for horses. Early airplanes carried mail and performed demonstrations before commercial passenger networks became practical. Electric vehicles grew first in markets, with charging infrastructure, subsidies, and customers willing to accept limitations. A flying car does not need to solve every transportation problem immediately. It needs one use case where its advantages are valuable enough to justify its costs. Tourism may provide that opening. A flight over a desert, coastline, lake, or mountain can be sold as an experience rather than a cheaper method of transportation. Emergency services could eventually value the ability to cross damaged roads. Remote industrial sites might use aircraft to inspect power lines, mines, pipelines, or large facilities. Islands and rural communities could use short aerial routes where bridges or roads are expensive. Each of these markets allows the technology to collect flight hours, improve reliability, train operators, and build public familiarity before attempting much more complicated urban operations. China is creating an unusually supportive environment for that process. Guangdong Province has announced plans to develop a major low-altitude economy cluster, with earlier policy targets placing the sector's scale above 300 billion yuan by 2026. Guangzhou, Shenzhen, Zhuhai, Hefei, and other cities have supported aircraft testing, manufacturing facilities, operating centers, tourism sites, drone logistics, and low-altitude infrastructure. In 2026, China's civil aviation regulator established a department focused on low-altitude safety, planning, flight service platforms, and coordination for manned and unmanned aircraft. This matters because the aircraft is only one part of the system. Cities also need landing areas, charging facilities, weather information, communication links, maintenance rules, insurance, emergency procedures, and traffic management software. A flying car without controlled airspace is simply an expensive machine with nowhere legal to fly. China's strategy is to develop the vehicles and the operating environment together. That coordinated approach does not guarantee the result will be safe or economically successful, but it can remove the institutional delays that destroy many new transportation projects before the technology has a chance to mature. The manufacturing strategy may be China's biggest advantage. AirAge's factory entered trial production in November 2025 and rolled out its first land aircraft carrier flying module. XPENG says the facility combines aviation-grade quality controls with automotive-style assembly methods. The initial annual capacity is planned at 5,000 aircraft, eventually rising to 10,000, with one aircraft leaving the line every 30 minutes at full production speed. The company also reported more than 7,000 orders as of late 2025. These figures come from XPENG and should not be treated as confirmed consumer deliveries. Orders may include institutional agreements, conditional commitments, or purchases dependent on certification. But the scale of the factory still matters. Most eVTOL companies manufacture a small number of aircraft using methods closer to aerospace workshops. China is trying to apply techniques learned from electric vehicles, standardized components, concentrated suppliers, automated production, rapid quality inspection, and high-volume assembly. If it works, the cost of building each aircraft could fall much faster than it would under traditional low-volume aviation manufacturing. If it fails, production speed could expose quality problems with consequences far more serious than defects in a car. This is the difficult balance nobody can avoid. Automotive manufacturing is built for scale. Aviation manufacturing is built for traceability and extreme caution. A car can contain a defective component and pull safely to the side of the road. An aircraft may not have that option. Aviation manufacturers document materials, tools, processes, software versions, technician actions, and the history of critical parts because investigators must be able to understand exactly what happened if something fails. Increasing production speed cannot weaken that discipline. One aircraft every 30 minutes sounds impressive, but the real measure will be whether every aircraft leaving the line matches the certified design. Batteries must perform consistently. Propellers must be balanced. Wiring must be protected from vibration. Software must be correctly installed. Structural bonds must survive repeated loading. Sensors must be calibrated. The hardest part of mass production is not building the first good aircraft. It is ensuring that aircraft number 5,000 behaves exactly as safely as aircraft number 1. This is where China's experiment becomes genuinely important. If AirAge combines automotive efficiency with aviation reliability, it could create a new manufacturing model. If quality varies under production pressure, the entire idea could lose public trust after a single serious accident. Battery technology creates another major limit. Electric motors are efficient, responsive, and mechanically simpler than combustion engines. They also make it possible to distribute propulsion across several rotors, creating redundancy. But batteries store much less usable energy per kilogram than aviation fuel. A road vehicle can carry a heavy battery because its wheels support the weight. An aircraft must lift every battery cell into the sky. Adding more battery increases range, but it also increases the energy required to lift the larger battery. Engineers quickly reach a point where each additional kilogram produces less benefit. Cold temperatures can reduce battery performance. Heat can accelerate degradation. Repeated high-power takeoffs can stress cells differently from normal electric car driving. Operators also need reserve energy for unexpected wind, route changes, or delayed landings. This is one reason the land aircraft carrier uses a separate ground vehicle to handle long-distance travel and recharging. The aircraft only needs enough energy for the aerial portion of the journey. That modular compromise does not solve battery physics, but it prevents the flying module from carrying the energy required for hundreds of kilometers of road travel. Weather is equally unforgiving. Promotional videos usually show aircraft flying in calm air beneath clear skies. Real customers face wind gusts, rain, fog, extreme heat, dust, and sudden changes in visibility. Small multicopter aircraft can react quickly to turbulence, but they also have less mass than conventional aircraft and may be affected more dramatically by changing wind. Heavy rain can influence sensors and electrical systems. Strong crosswinds can make vertical landing difficult. High temperatures reduce air density, which means rotors must work harder to produce the same lift. Cold weather affects batteries. Mountain areas create complex airflow, even though those are exactly the scenic locations where customers may want to fly. A practical flying car service will need strict operating limits and reliable weather information. That could mean many flights are canceled on days when cars continue operating normally. Customers may accept that limitation for recreational flying. They are less likely to accept it for daily transportation. The dream of escaping traffic only works if the aircraft is available when people need it, not merely when the weather is perfect. Then there is noise. Electric aircraft are often described as quiet because they do not use jet engines or large piston engines. But quiet does not mean silent. Rotors repeatedly cutting through the air produce a distinctive sound, and multiple aircraft operating over the same neighborhood could become irritating even when each one is quieter than a helicopter. Frequency matters as much as volume. A sound that is technically below a regulatory limit can still be disturbing if it occurs every few minutes. Cities will have to decide where aircraft can fly, how high they must remain when operations are permitted, and how routes avoid schools, hospitals, residential buildings, and protected areas. The FAA in the United States has created operational rules for powered lift aircraft and is developing infrastructure guidance. But American companies are still moving through aircraft certification. China has moved earlier in approving a pilotless passenger eVTOL for controlled services, while the United States may take a more gradual path through piloted aircraft and existing aviation structures. Neither approach has proved it can support thousands of daily urban flights. The winner will not be the country that stages the most dramatic demonstration. It will be the one that earns public acceptance while maintaining safety. Cost may determine the outcome before technology does. Early flying vehicles will not be affordable replacements for normal cars. Carbon fiber structures, aviation electronics, redundant motors, certified batteries, maintenance, insurance, training, and specialized infrastructure are expensive. Even after purchasing the aircraft, owners will need approved places to operate it and technicians qualified to maintain it. Parts with limited service lives may have to be replaced according to schedule even when they appear functional. Software systems will require monitoring and updates. Batteries will eventually lose capacity. For commercial operators, the aircraft must fly often enough to recover those costs. A machine that spends most of its life stored inside a carrier may be exciting but financially inefficient. That is why tourism, government services, industrial inspection, and premium experiences may arrive before inexpensive urban commuting. These markets can charge more per flight and operate from controlled locations. Mass production could lower the purchase price, but it cannot eliminate aviation's operating costs. Flying cars may become real long before they become common. The first customers will probably not be ordinary workers escaping traffic. They will be businesses, governments, tourism operators, and wealthy enthusiasts willing to pay for access to the sky. International expansion will create another barrier. Certification issued in China does not automatically allow an aircraft to carry passengers in the United States, Europe, Japan, or other countries. Each aviation authority may require validation, additional testing, operational restrictions, or changes to the design. Regulators may evaluate autonomous flight differently. Countries may be uncomfortable, allowing an aircraft controlled by software and remote communication systems developed abroad. Cybersecurity will be a serious concern because a connected aircraft depends on navigation data, software integrity, communication links, and ground systems. Manufacturers will need to demonstrate that attackers cannot take control, manipulate routes, interfere with positioning, or disable fleet management systems. China may create a successful domestic industry while facing restrictions overseas, just as its telecommunications and drone companies have encountered political resistance. But the domestic market may be large enough to support the industry during that process. AirEdge does not need immediate approval in every Western capital to continue developing the vehicle. It needs enough Chinese operating sites, customers, and production volume to improve the technology and prove that the business model works. So, is China's flying car truly no longer science fiction? The honest answer is yes, but not in the way movies promised. There is no vehicle rising automatically from a traffic jam and carrying its owner directly to an office balcony. China has built something less magical and far more credible. A road vehicle that transports, stores, and charges a detachable electric aircraft. A dedicated factory has entered trial production. The company is preparing for large-scale manufacturing. Another Chinese eVTOL has already completed a major certification pathway and received approval for limited commercial passenger operations. Local governments are developing low-altitude infrastructure and regulation. These are real industrial steps, not computer-generated concepts, but the technology remains early. Certification, weather, noise, batteries, maintenance, airspace management, cost, and public trust will determine whether the first production vehicles become the beginning of a transportation revolution or expensive machines used at a small number of tourism sites. The aircraft exists. The factory exists. The regulatory pathway exists. What has not yet been proven is whether the complete system can operate safely and economically at scale. That is the real story hiding behind the futuristic design. China did not solve flying cars by inventing a machine that performs every task perfectly. It separated the problem into pieces. Let the road vehicle handle distance, energy, storage, and bad weather. Let the aircraft handle short flights. Let software reduce the difficulty of control. Let controlled tourism routes build experience before crowded urban routes. Let automotive manufacturing lower costs while aviation certification protects safety. Every one of those steps could still fail, but together they create a path that did not exist when flying cars were only displayed at exhibitions. The most important question is no longer whether China can make a vehicle leave the ground. It already has. The question is whether it can build thousands of them, certify them, maintain them, create legal places to fly them, and convince passengers that stepping inside is no more frightening than entering a car. If China succeeds, the future will not arrive with every automobile suddenly growing wings. It will arrive slowly. One approved route, one factory line, and one carefully controlled flight at a time.